electronics. And this is a joint work with my former student, Jiao Qi Dong, who is now postdoc in NYU, Abu Dhabi. Okay. So this is more or less the plan of my talk. I will first make an introduction, talk about some modeling, and then I will give the main result. And then I will first suggest a formal approach for the proof, and then the rigorous proof. At the end, if I have time, I will give some details about some part, the main part of the proof. Okay, so MEMS, as Nabil kindly explained 2 minutes ago, stands for micro electromechanical system. And this is in fact an electronic device which has two components. The green one here, which is a rigid plate, okay, and above it, okay, we have an elastic membrane. So in fact, this membrane will uh, move, okay, on the contrary of the rigid plate, and both are connected to some source of electricity and a capacitor. Okay, so we can find this kind of device in very familiar in many familiar devices such that microphones, transducers, sensors, etc. The idea is the following. For example, if you talk in front of the membrane, then you make the membrane move, and then this movement, this motion of the membrane will be translated in some electrical signal, and that's basically, roughly speaking, the way the microphone works. Okay, this drawing is not mine. It comes from the following authors, which I thank. I would like also to give some references, mainly math papers about MEMS. So this one by Flores, Mercado, Perezco, Smith, Guo and Suple, Cavalaris and Suzuki in their book. They have a book dedicated to this problem, Guo and Yu, and also STV and Suple, just to mention some of them. And by the way, this is a drawing from the PhD thesis of Carlos Esteve, who was a PhD student in our lab in Sorbonne, Paris Nord. So here he made a different drawing. The rigid plate now is yellow, it is above, and the membrane is in the bottom. And now we are normalizing, in fact, the distance between the rigid plate, sorry, yes, and the membrane to 1, okay, when it is at rest, when the membrane is not working. In fact, when we don't have electricity somehow, we are not using the device. And then when we are using the device, this distance between the membrane and the rigid plate will change. It will become u of x and t. So it depends on x, which is the space, and also time. And it will be always between 0 and 1. You see that I have changed the orientation here. We had the membrane on top, and now it is on the bottom. But of course, we have no gravity here. I mean, we can neglect it anyway. The first model is a hyperbolic equation, and this is reasonable, of course. Why? Because if u is the movement, the motion of the membrane, then this is the acceleration and this is the velocity. Okay, so you see that applying Newton's principle, you can write this kind of equation when you have all the forces that are applied to the system, to your membrane. Okay, and here I just draw your attention to the fact that I have here epsilon square. Of course, epsilon is something small. If you divide all the equation by epsilon square, then you will get here 1, and here in front of the velocity 1 over epsilon square. This is friction, in fact. So somehow we will be in the limit where epsilon goes to 0, which means that the friction is very high. I would like to draw your attention to the fact that here I have a term which is in 1 over 1 minus u square, which means that when u, sorry, I will try to go back. When u goes to 1, which means that the membrane touches the rigid plate, I have in this term which becomes infinite. And this is in fact the phenomenon I am looking for. Here I am on a bounded domain omega of Rn. I have Dirichlet zero Dirichlet boundary conditions and initial data. Now, as I was saying, I will take the limit really epsilon equals to 0. When epsilon is equal to 0,
Sorry.
I have, yes, go ahead.
Uh,
Is there
can
a
you give
question?
some? Yeah, yeah. Please, can yeah, please here. Uh, you have initial data u0, right?
Absolutely.
But you have like hyperbolic equation like ddu.
Oh, you are completely right. Yes, yes. This is a big mistake. Of course, yes,
Oh,
yes,
okay.
Makram. This is Makram, of course. Yes.
Yes, yes,
Yeah.
yes.
Okay. I see your name showing. Of course, you are completely right. I need also initial data for the velocity dtu
Yes.
equals some u1. Of course, here there is a large theory to the hyperbolic equations, but in fact, this hyperbolic equation, although it is more realistic, in fact, it's less tractable from a mathematical point of view.
Mm.
But for sure, I think in the book by Suzuki and Cavalaris, you probably will see some good mathematics, at least for the Cauchy problem for this.
Okay.
I will correct my slides
No, no, no
afterwards,
problem.
Mac.
I
Not
guess you
now,
are thinking
not now.
about the limit when epsilon goes zero, so it will disappear this this
Absolutely.
initial data. Yeah. Okay. Thank you. Thank
Absolutely.
you.
Yeah, yeah, you're welcome. But in fact, going back to this slide, I figure out that I forgot something extremely important for me. Here in this term, I have a non-local term. Here we have the integral over omega of 1 over 1 minus u, which means when u goes to 1, which means that the membrane goes to the rigid plate, this term at least under the integral sign will go to infinity. But so we don't know if the integral will go or not to infinity, but anyway, this is a non-local PDE, and this is in fact the difficulty of the situation. Now I go, as I said earlier, to the parabolic limit when we take epsilon rigorously equal to 0. I also take f, which is equal to 1, this guy, okay, and gamma positive. In this case, this is the parabolic PDE that we end with. And once again, we have a non-local term. And this time, for initial data, we only need one uh, uh, initial data for U0. Remark, this is a non-local parabolic equation, and this is the difficulty, in fact. Now, I would like to go back to electronics and talk about the touchdown phenomenon. So, in fact, when you solve the Cauchy problem, which is in fact easy, this is not the issue, either your solution is global in time, which means that here u is never equal to 1, okay? But if ever u becomes close to 1, okay, then you may have the finite time existence, which means that we have some capital T such that the solution exists only on omega times 0 capital T. And in fact, when T approaches capital T, the minimum of 1 minus u, which is the distance between the rigid plate here and the membrane here, this means that the distance goes to 0. If this guy will converge to 0, at least for a subsequence, we say that we have a touchdown. Why? Because in fact, I would like to go to the first picture, this one, where the membrane is above and the rigid plate is at the bottom. So you see that the membrane touches down the plate. Of course, here Carlos Esteve made a different orientation, and I'm using his orientation at least for the beginning of my talk. But yes, in the literature, people often talk about touchdown, in fact. Okay, uh, in some other papers, not necessarily related to the MEMS, in particular with no non-local terms, some authors are mentioning finite time quenching. This is just some vocabulary. Okay, so I already said all this. Yeah, okay, I forgot that he had this picture here. Okay, same reference. And in that case, in fact, but this is extremely important, if ever we have this touchdown, the MEMS device will be broken because, okay, we will have an electrical problem there. Now we will define the touchdown time. This is the maximum existence time because the solution stops from existing at that time. Okay, but then x0 is the point where the membrane touches the rigid plate. Mathematically, okay, well, people may say the following: u of x0 and t goes to infinity, but this is not good, in fact, because if you are not at if you are at a regular point where you don't have touchdown, then you will not have a nice bound locally. So in order to have a nice bound outside the touchdown points, we need to give this general uh, definition of a touchdown point where we have a subsequence xn, tn, converging to x0 capital T, where we have this touchdown. Okay, what's my aim here in this talk? We would like to construct a solution, to give an example. In fact, I am not saying that I take any general solution which has touchdown and I will describe it. No, unfortunately, no. But I will at least give an example of a solution which has this touchdown phenomena and only at one touchdown point x0. In that case, we will in fact have this convergence for all sequence t, okay, or any sequence tn, in fact, okay, goes to one at this x0. And I will try also to describe the shape of the solution around x0. And this is what we call, in fact, the profile phi of x. So you know 1 minus ux t when ux capital T is the limit, in fact, of the membrane. This limit will be equal to 0, in fact, at x0, and outside x0 it will not be 0 because x0 will be the only touchdown point. Well, it will have some profile. It's approaching 0, this guy, okay, this distance. We will try to find the profile, in fact, near the singularity which occurs at x0. Let me now mention some earlier results. For example, we have these authors, Guo, Yu, and Wang, who proved that, in fact, we have this lower bound on phi of x. Later in our results, we will have an equivalent of phi, and which will be with x to the power 2/3 with some logarithmic corrections. So we are improving this result. We also have some sufficient conditions for touchdown by Guo and Cavaleris, which say, okay, when omega is small, the size of the device, in fact, is small and gamma is positive, then we have touchdown. And then also we have an estimate by Guo and Yu of the touchdown rate, because at 0, or this distance goes to 0, okay, but at which rate? Uh, these authors already have it. It's capital T minus T to the power 1/3. We will confirm, in fact, this rate, at least for our example. Now I will give the main result of our paper. which uh, had already appeared, I think, maybe not in 2019, maybe 2020. I have to check, maybe 2019. Okay, so yes, there is a touchdown solution with only one touchdown point, the origin, because I take omega, which contains the origin, at some time, capital T, and now I have two notions of profiles. The first is what I call an intermediate profile. Look, this guy is the distance between the rigid plate and the membrane. It goes to zero. I'm trying to compare it to this rate. We already know from earlier results that this is a good rate, in fact, for the distance. And this is good news because we see that when we make this ratio with exactly 1/3 here, we find a limit. We see some profile, in fact. This profile is in the reduced variable, which is x divided by the square root of capital T minus T log of capital T minus T. It is bump shaped, in fact. So yes, we will see a kind of intermediate profile. You will see that this rate divided by this distance will have this shape of a bump with the width of the bump going to zero. And of course, very important here, we have some constant theta star, which is present here. Now, I will talk about the final profile. I will take, in fact, the, uh, the limit of the membrane when T goes to capital T. If I'm at zero, the origin, this limit will go to one, okay? But which is the only touchdown point for me, the origin. Outside the origin, I will converge to some uh, u star of x, and this u star of x will be equal to one only at the origin, and outside the origin, it will have this shape. Okay, it will not be zero. Okay, so we have x to the power 2/3 with a logarithmic correction. Okay, so this is what happens for the final profile, and I will give some comments on this result. So first of all, the final profile is a cusp. It's not C1 because we have x to the power 2/3, which is less than 1. Second, of course, by simple translation, we may take the solution, we may make the solution touch down at any other point x0 in omega. Okay, and of course, also in the case where omega does not contain the origin. Then we are also able to use a technique by Merle in CPAM 1992, old paper, where he could start from a solution which blows up only at one point and then make some gluing to make the solution blow up at some arbitrary given x1, xk, infinite number with any, any points chosen in this domain. Now I would like also to talk about the touchdown rate at the touchdown point. Yes, it is given by capital T minus T to the power 1/3, as people did already proved in earlier literature. And now I have some open question. Can we construct a touchdown solution with a prescribed theta star? Let me go back to the previous slide to comment a little bit more about this. Here, I would say capital T is time, okay, but here uh, everything is known. I would like to say in this formula except this theta star, which is unknown. It's given as a product of the proof. But my question, can we say that for any theta star positive, we can find a solution, okay, such that we have exactly this with this very same theta star, which was given from the beginning? Well, we don't know, but we think that this is possible, in fact, and we make this conjecture, yes, but not for any theta star, maybe starting from some minimal theta star. Now I would like to announce some new result. Okay, it's by Dong Cavaleris and myself, which is on archive, and we could in fact construct a blow-up solution. I say really a blow-up solution for this related non-local PDE. So roughly speaking, if you ignore this integral here, you have the semilinear heat equation with power nonlinearity, because if we have blow up, this UP, if P is more than one, will be dominant with respect to this U. So you can ignore it anyway. Okay. So in fact, with my co-authors, we tried to see if the fact that we have a non-local term can change or not the proof. And in fact, it was a challenge for us, and we could obtain similar results with similar profiles somehow. Of course, this is possible in the subcritical case, which I define like that: r divided by p minus 1 is less than n over 2. And also we need gamma r to be different from p minus 1. This model is not just mathematical, it comes from the Gierer-Meinhardt system, okay, which is in fact a system. We make a singular limit and we take the so-called shadow limit and we end up with this PDE. One thing I should have noted here, in fact, this Gierer-Meinhardt system is linked to the Turing phenomena of activator inhibitor systems in reaction diffusion systems to, for example, explain the skin of some animals, etc. So this Turing phenomenon, and we end up with something like that. You can see more details about physics in this in our paper, but mainly in the literature, in the great literature by Nikos Kavaleris. In fact, he is really an expert on this subject. There is also some other work I would like to mention by Buthayna Abdelhadi and myself, which is to appear in Journal of Differential Equation this year, hopefully, and which is related to the following PDE. So the interest of this PDE is that we have two difficulties somehow. We first have some gradient term, okay, which implies that we will for sure need parabolic regularity to control our solution near the blower profile. But we also have a non-local term, and this non-local term is not integrated on the whole space, but only in the ball of radius norm of x, the modulus of x. Okay, so we could succeed, roughly speaking, with Buthayna. We could say that we have an example of a solution which behaves like the solution of the semilinear heat equation, which means that, in fact, we were in some case where this term, although very nasty, was subcritical in size with respect to u to the power p. Now, following our existence theorem, we have a stability theorem. Let me state it like that. From theorem 1, we have a solution which I will write as u hat with initial data u0 hat, a touchdown time t hat, a touchdown point a hat, and the profile parameter theta star hat. Okay, let me go back a little bit. Yeah, you see, this is the parameter. And when I say that we have a touchdown point a hat, this means that here it's x minus a hat square. And same here. Okay, so assume that you have a solution like that. It is an example, constructed example. Then the question, if we perturb a little bit initial data, can we have still the same phenomena? And the answer is yes. The new solution with the new initial data u0, which is close to u0 hat, will also touch down at some time, which is t sub u naught, at some point a sub u naught, with the same profile, in fact, showing a different profile parameter. Not necessarily the same, but we have this, in fact, continuity result, meaning that the blow-up features will be close to the blow-up features of my reference solution. Okay, so in fact, this existence result uses the reduction to n+1 dimensional problem, a finite dimensional problem, in fact. And in fact, this is, in fact, the dimension of the geometric features of the blow-up problem. Why? Because in my blow-up problem, I have a time for touchdown or blow-up. When I say blow-up, it's 1 over the distance, which blows up, in fact, which is 1 dimension, and also the touchdown point, which has n dimensions. Okay, so in fact, because uh, my existence result reduces to n+1 dimensions, and that n+1 is the dimension of the geometric features of the problem, since both are equal, in fact, I can have the stability result as a byproduct of the existence product result. I mean that the key estimate here is to find an example, but once you have an example, you will easily see that your existence proof is also a stability proof. Now I would like to give you a formal approach. The difficulty, as I already said, is because we have this non-local term. So let me introduce now V, which is 1 minus U, the distance between the rigid plate and the membrane. And then I will introduce alpha of V, which is this non-local term. Then immediately my equation becomes the following. dTV equals Laplacian V minus alpha over V squared. And alpha depends on the solution, and it depends on the solution thanks to its integral, to this integral, in fact. So here, the goal becomes to construct a solution to this equation such that V goes to 0, where V is the distance between the rigid plate and the membrane. Okay, now let me try to see some special cases. The first special case for me is the case where gamma is 0, in fact. If gamma is 0, of course, everything will depend on the behavior of alpha. If gamma is 0, or if we replace alpha of V by constant, then we see a very familiar heat equation. This heat equation is not a heat equation that gives blow up. It's a heat equation that gives quenching, because the problem is not when V goes to infinity, it's when V goes to 0, okay? And a long time ago, with Frank Merle, we could have the following result, which is, yes, we can construct for this PDE a solution which has this profile, okay? So when t is between 0 and capital T, you see that the shape of V is the following. It's a bump centered at the origin. And uh, I mean, it's a bump, but in the other way, in fact, it's a kind of positive parabola. So the minimum of this shape goes to 0, and then we have some rate for the width of the profile, which obeys to some reduced variable, which is x squared divided by square root of capital T minus T log of capital T minus T. Okay. So you will see that only at the origin we will go to 0, and outside the origin we will not go to 0. And this is in fact easier to see in the final profile, So when t goes to capital T, we converge to some profile V star, and this V star has this shape. So it is equal to 0 at the origin, because this is the only quenching point or touchdown point, and outside of it, it's not 0. We don't have touchdown, but we have this kind of singularity. And it is, once again, it's a cusp, not C1. Now I would like to take another case, the case where alpha of V is replaced by some alpha of T, which does not depend on the equation, which converges to some alpha 0 positive. Okay, so in some sense, we have a perturbation of the simple case where alpha is equal to alpha 0. So if you have alpha of T here, which is close to some alpha 0, it's straightforward to see that it's by a small perturbative argument you will have uh, the solution. Okay, and now I would like to move to our case and try to write it, at least formally, as a perturbation of the simple case. So let me first write it as a system, and this is in fact an important idea because somehow I will try to make a decoupling between in my system between a PDE and a polynomial equation, in fact. So look, this is just formal. This is exactly my system, okay? Which I have just wrote 2 slides ago, okay? Now, the idea is the following. We will, in fact, try to construct our solution and try to be careful so that this alpha, this theta of t will converge to some theta 0 positive. So if we can do that, look here, you will have alpha 0 over v square. It's exactly the case that I mentioned before. So this is good, in fact, because we have a machinery to treat that. But in fact, when you have this theta 0, we would like to have theta 0 equals to 1, in fact. And this is easy to recover if we make a small scaling uh, in our problem. And this is in fact what we will do. We will introduce capital V, which is theta t to the power negative 1/3 multiplied by V, okay? And if you do that with theta of t, which is constant, you immediately recover the case where theta is equal to 1. So this is a reasonable change of variable, but now theta changes. So if it changes, we'll recover some perturbation term, which I will write here. You look, if theta is a constant, you don't have this, and you have exactly the equation with the constant equal to 1. Now, because we have this the theta which depends on t, we will have this term. And then, in fact, I make a small, reasonable rewriting of my second equation. Let me go back a little bit. Here you see theta is given in terms of 1 over small v. But if I replace small v by capital V and theta, then in fact the second equation transforms into a kind of algebraic equation for theta of t if capital V is given. And our goal was, in fact, to have small v which goes to 0. Now, small v is theta to the power 1/3 capital V which goes to 0. This is still my goal only at the origin when x is equal to 0. And okay, this is the remark. If you write lambda of t, which is theta to the power negative 1/3, you see from this second equation that lambda satisfies a polynomial equation where one of its coefficient, at least, or in fact two, depend on this non-local term, in fact. So this is good news somehow. If I can succeed in constructing capital V, then I will immediately solve for lambda, and then have theta. But of course, if you want to construct for capital V, you need also to know about theta. So of course, there is a decoupling. There is coupling, but we will try to decouple things. We'll see. Okay. So this is the reduced problem. You see theta is here and here. Okay. And this is the goal. And we will stick to our idea of making theta converge to theta 0, because we would like to be in some perturbative uh, uh, way for our approach. And of course, we will also try to have theta prime which goes to 0, which is reasonable given this, no oscillation somehow. So our goal becomes to have, in fact, capital V which goes to 0. Okay. And small hint, let us think, make a dream, if this term is negligible with respect to this one. Then we end up with the following question. We have this PDE where we neglected the other term, and we have this polynomial equation. So our system is decoupled somehow, and we can try to apply the machinery that we have for this PDE to have a solution for this PDE, but of course we have some perturbations. So we will see. So let's start with the first equation. This is the PDE with a perturbative term, which is more or less equal to this, and we can use the old machinery of 1997, and we will have this intermediate profile. I already gave that, this final profile, and this is good. Okay, so this is a cusp once again. And now I would like to move to the polynomial equation satisfied by lambda t. This is the polynomial equation where the integral of 1 over v is one of the coefficients. So let's try to estimate now the integral of 1 over v. This is 1 over v of x and t. So we can in fact say that it will be close to the integral of 1 over v star, which is the final profile, which is a cusp. But in fact, we are lucky, in fact, because we find here that the inverse of the cusp is integrable, in fact. So we can have in any dimensions, by the way. Okay, so since it is integrable, it's reasonable to say that lambda of t will converge to the solution of the same polynomial equation where I replace v by v star. And it's not difficult to see that we have a solution which is not 0. In fact, no solution can be 0, in fact, here. And which means that lambda will converge to lambda 0 positive, and theta will converge to theta 0 positive. And now, because 1 minus u is equal to v, which is the distance between the rigid plate and the membrane, which is equal to this guy, v goes to 0. We have a profile for v. We know the behavior of theta, so we know everything about u. And we are done. Now I move to the rigorous proof. I hope I have time to mention something about it. Well, I will try. In fact, here we have a very robust method, which, up to my knowledge, goes back to Bressan in 1990, Bricmont and Kupiainen in 94. I also did it with Frank Merle in 1997, and there are many other papers that I will mention, in fact. This is at least for the standard semilinear heat equation. What is it about? It has two parts. First, the construction of an approximation, okay, which is in fact a candidate for the profile, and this was the formal approach. I already gave you some hints about that. But when you have a candidate for the profile, now you move to a rigorous approach where you linearize around the profile, okay? okay? And you try to show that the linearized PDE has a solution converging to zero. And this is a rigorous proof where we have still two steps. First, we reduce the problem to a finite dimensional one. Roughly speaking, we have a linear operator, so we will see a negative part of the spectrum where we will try to control it with the decaying properties of the fundamental solution of the Laplace operator, in fact, and we are left with some parameters which correspond to the positive part of the spectrum, eigenvalues, in fact, and then we will use degree theory to solve the finite dimensional problem. Earlier and non-exhaustive literature, and I have to thank my former student Vantine Nguyen, who is also in NYU Abu Dhabi, but soon in Shanghai. No, not Shanghai, Taiwan, in fact. Yes, he is going to move to Taiwan very in summer, I think. The idea is how to construct a solution for PDEs with some prescribed behavior. Okay, and Vantine did a great job because he gave me this huge bibliography, have many people. I will mention nobody because I cannot mention everybody. So just see by yourself some names. Okay, we can have for critical, subcritical, supercritical, type 1, type 2. I don't want to go into details. You have people who do similar things for NLS, wave type equations, and also other equations, including fluids, including Keller-Seeger for chemotaxis, etc. Okay, now let me make a change of variable. Okay, I have U bar, so trust me, this is really a very basic algebra, which is now U over U minus U. So it will go to infinity, in fact. And this is the non-local term. So, and now I make the scaling with this theta bar, okay? All these techniques have been already used during the formal approach, more or less. So when I do this, I end up with this equation on capital U. So capital U, first of all, will have to blow up. Okay. In fact, I personally like blow up problems with respect to quenching problems. So probably this is the explanation why we do that. Okay. So we have this term which was neglected earlier. Here u will go to infinity. So this is more or less u to the power 4. This is more or less gradient u square over u. Okay. And this is, of course, our non-local term, but we will uh, do our best to have this theta bar go to some positive constant limit. So in fact, when this goes to a positive limit, you will see that we can neglect this three terms, and we will be left now with a solution, sorry, yeah, which is more or less this one, in fact. Okay, let me go back a little bit to say that constructing a touchdown solution U for small u is equivalent to constructing a blow-up solution capital U. In fact, we have this twin equation, which is, in fact, I forgot here, the -2 gradient U square over U. We can put it. In fact, with gradient U square over U or without it, it's more or less the same thing, but technically it's much, much more difficult when you have gradient U square over U. But more or less, we are in this framework. And in this framework, we have a machinery which uses similarity variables, first introduced by Giga and Cohn here. So I make this change of variables. So in fact, I want u to go to infinity when I multiplied by this guy. Okay, here there is a mistake. This should be +1. I expect W to be bounded. This is also a slow time to the singularity, and this is a zoom near the origin, near the place where we will have singularity, and it's a zoom in parabolic style because I have square root of capital T minus T. This is the equation in similarity variables. Okay, I write it like that. Trust me, this is exactly what you obtain with a very simple algebra. So the time derivative of u with respect to t will generate three terms, this one, and this one, and this one. Okay, the others are easier, in fact, to see. One comment, the domain is extending, in fact. This is defined on some omega sub s, which grows exponentially. Okay, and I have here a t bar, it's a theta of s, which is t bar of t of s, okay? And this is my non-local term. So I have always to use both formulations, either with capital U or with capital W. Everything will be important. Okay, so once again, theta bar solves a polynomial equation if U is given, okay? So this is the equation. And the idea now is to find a solution for this PDE. And this PDE, as I said earlier, has a time which goes to infinity. And this PDE will have a W which will be bounded because I have a plus here, in fact. So we will find a solution for this equation with some prescribed behavior. As I said earlier, because theta will go to a constant and theta prime will go to 0, in fact, all these will be small terms, in fact. So I reduce to the case where I have only this equation, and this equation is exactly the same that was treated in 1997 in this paper. So the idea will be to control the perturbation, making some a priori estimates, the good a priori estimates to make theta close to some theta 0 and make theta prime over theta go to 0 exponentially fast. And if we do it, then we will see that the machinery, the old machinery will apply. And the old machinery gave us this profile. Okay, so we are able to use this PDE with the sign equal here and to have this profile. The challenge now is to take this PDE with good a priori estimates and still to have the same profile. Perturbative, but not naive, in fact. Here, we will have, in fact, three ansatz, three controls of the solution of the PDE in three different regions. Okay. The first region, which is inside this variable, I mentioned many times x divided by this. So when you are in this means that this is y less than k0 square root of s. We will take this ansatz for the unperturbed equation. If we are in some intermediate region, we escape the place where this is valid, okay? And we will go up to some x equal to epsilon 0. We'll say that u is close to the final profile, the cusp. Okay, the cusp is not a good approximation inside, but in this intermediate place, it's a good approximation. And outside epsilon 0, we'll simply take u0 as a good approximation for our solution. Why? Because in fact, here capital T will be very small. So it will not change a lot outside this ball of radius epsilon 0 over 4. Of course, this is over 4, this is over 1, this is over 4. We need some overlapping between the three regions. And we will also make the following control, theta prime less than some exponential. When you do this, theta will immediately converge. So if initially it's far from zero, it will converge to something which is still far from zero. And now I will try to see what time is it. Probably I will stop here because I ran out of time. Okay, thank you for your attention.
Thank you, Hatem. Perhaps you can just give some words about the last section very quickly.
Okay, thank you. You are extremely kind with me, which means that you are giving me some more minutes. So I will not take a lot of minutes, maybe 2 or 3. Nabil, if you don't mind. Thank you. So I will to start with the control in the inner region. In fact, yes. So, and I will only do the control in the inner region. We want W to be close to phi. Okay. Yeah, this is phi. Okay. So what to do? Simply linearize around phi. Introduce Q, which is W minus phi, and now we would like to have Q, which goes to 0. This is our aim. And then we write this equation. Well, you will tell me this is horrible, and you are right. But let's try quickly to say what we have here. Here we have some term here, which means that phi is not an exact solution. This profile is not an exact solution of my PDE. It's an approximation. So this is not 0, but it's small. So this guy will be small. Good. This guy is in fact quadratic because we are making a linearization of the nonlinear term. So if it is quadratic, it will be negligible with respect to the linear term. This guy also, we can ignore it somehow. It will be small. We don't make a Taylor expansion of order 2. So in fact, all will reduce to this guy. If we understand the profile, the linear operator, then we know everything. And in fact, here we have a potential. Why we have a potential? Because the potential comes from the linearization of the nonlinear term. So now I will go a little more quickly. This L plus V, you can simply assume that you have only this PDE. All other terms equal to 0. Just to understand, it has two important properties. When y goes to infinity, okay, in this region, in fact, v will lower, okay, the highest eigenvalue of L, because the highest eigenvalue of L is 1, and v will converge to negative 4 over 3. So all this will behave like an operator with a highest eigenvalue, which is 1 minus 4 over 3, which is negative. So we will not care about the part of the equation in this place. Okay. Then inside, v will be small, so we will care only about L. And L, in fact, okay, it has, yes, this spectrum, L, which has 1, 1/2, and 0. Okay. So we will, and then negative 1/2, negative 1, negative 3/2, which are negative. So in fact, we will not care about, sorry, of course, the eigenfunctions are given by Hermite polynomials. Okay, very easy. In one space dimension, that's 1, y, and y squared negative 2. Okay, so in fact, we will not care about Q minus because it's the negative part of the spectrum. You start small, you stay small. So that's how we reduce to only 3 components, finite dimensions. This is crucial. Let me start with Q2 because it comes with lambda equals 0. So because lambda for L, this is lambda equals 0, we have to use the potential, which I neglected. The potential comes with a kind of eigenvalue which is -2/s, which will go to 0. But here we will introduce a slow variable tau, which is log of s, and you see that this equation transforms in the following, which has a negative eigenvalue. So you start small, you stay small. Okay, so we are left only with q0 and q1. Okay, and we can write the equation satisfied by q0 and q1. Here you see lambda equals 1. Here you see lambda equals 1/2. You may add here even artificially, but in fact they are here quadratic terms in q0 and q1. Any quadratic term. This is a baby problem, just to make it a coupled system. And you can use, in fact, degree theory, Brouwer theorem, to find initial data such that the solution of this system goes to 0, because this is not the case for any initial data. If you take initial data which is very large for q0, very large for q1, you will go to infinity and never to 0. So you have to fine tune somehow, and degree theory is very important. Okay, and this way the only problem is with expanding eigenvalues. So we have a solution which goes to 0, and I'm done. So thank you, Nabil. You gave me, I took maybe 5 minutes. I'm sorry. Thank you.
Okay, thank you very much, Hatem. If there is some questions, please. No questions? Okay, I have a little question about the
Yes,
model that you use.
of course.
Perhaps you said, what is it? But what is epsilon? This little parameter in the model.
Yeah, let me go back to the model. Sorry, yeah, it's probably here. Oh, yes. In fact, this is.
I mean in the experience. No,
I understand. I
okay,
understand.
okay, okay.
Yeah. I understand your question. Of course, here x and t are probably not the original. How to say? Uh, let me think a little bit. Yeah. So now we will divide this equation by epsilon square. You will recover 1 here, and 1 over epsilon square, and 1 over epsilon square here. Here, if you change, you take a new variable, which is epsilon x, then you will recover Laplacian, not 1 over epsilon square Laplacian. So the physicists, up to my knowledge, who write the first equation was the following. This is with 1, and this is with a large coefficient, which may be written as 1 over epsilon square, and here a not very large coefficient. But then, in fact, you make some scaling to make this equal to 1. Okay, and in fact, this coefficient is the friction. So if we write as 1 over
Which one? The epsilon or 1 over epsilon? The friction.
1 over epsilon square in
Okay.
front of the velocity. In front of the velocity, because I think that the first model is the following: second derivative in time plus 1 over epsilon square, because friction is high, equal to some constant multiplied by Laplacian u. Then we change omega, we make a scaling to make this constant in front of the Laplacian equal to 1, and then we will see that we have a large friction coefficient. In fact, yes, we have friction in these devices, and that's why, in fact, the parabolic limit is reasonable, because if friction is not high, you cannot reduce to the parabolic limit. The parabolic limit will be useless from a physical point of view, but up to my knowledge, it's really reasonable, in fact.
Okay, understand. Then when the friction is not high, it's vibration, and when there is a big friction, it's heat transfer equation.
Exactly. Yes. But if friction is not very high, then the problem is much more difficult. And for me, it's an open problem to construct something, a solution with the description of its touchdown profile. Yeah.
Okay, thank you, thank you.
Thank you, Nabil.
Yes, Muhammad Ali, of course. Perhaps.
Hatem, how are
Oui,
you?
Muhammad Ali.
Thank you for this nice presentation. It was
Thank you for
clear.
listening.
I have just one question.
Please.
If I understand well, the situation is the profile is like the case when gamma equals 0. Is it possible to construct some profile when we have a competition between the local term and the non-local term? And,
Absolutely. Yes, this is a very good question. In fact, here, we may replace this 2 by some q, and this is by some r. And in fact, when q is equal to 2 and r is equal to 2, we are in some subcritical case, okay? Which means that this integral will converge, in fact, will be converging, and this guy will converge to a constant. But you have a critical case where this guy will not converge to a constant. And in that case, you will have a competition. And that competition can be seen, sorry, I would like to mention the remark. Yeah, maybe it will be much more clear in this, sorry. Yes, exactly. In this work with Dong and Cavalaris, look, Muhammad Ali, your question can be stated for this PDE, and what you are saying is the following simply. What happens if R over P minus 1 is equal to N over 2? This is our next challenge, and we are working hardly to get that case. It's much more difficult, in fact, yeah. And of course, yeah, but I think it's reasonable to find something. Of course, later you may think of the case where we have supercritical, where this is larger than N over 2, and in that case, it will be somehow the effect of the non-local term will be much more important than the reaction term, the U to the P.
just there are any idea about the proposed profile, the possible profiles?
You mean in the critical or in the supercritical?
In the critical, at least.
Yes, because we are working on that, in fact.
Okay, okay. Thank you.
You're
Good luck.
welcome. Yeah,
Okay.
thank you. Yeah, it will be something which is which will have some corrections in the rate with respect to what we know for this subcritical case. Yeah.
Thank you.
Okay, thank you. I think Fathi have a question.
Yes, thank you, Nabil. Thank you, Dr. Hatem, for the nice presentation.
Thank you, Fathi.
Nice
to see you.
Okay, nice to see you as well. If I think about it, this is like a novice's question.
Yes.
If I think about it, I think one of the to me, after the
Yes.
lecture, the whole thing surrounds around one main equation, which is dv, or the time derivative of v equal to Laplacian minus alpha over v square.
Yes.
Okay.
Yeah.
So if I were to be, suppose, I'm not like rigorously mathematical or whatever. If I were to multiply by v square throughout,
yes,
then I would get v square multiplied by the operator derivative of t and minus Laplacian, yes?
Absolutely, yes.
Okay, so I would look like at this operator to v cube, and this I'm trying to find out where the minus 1/3 is coming from. So if I do,
yes,
you understand?
Yeah, I understand.
Forget, and also there is one critical thing about the derivative, about the when division at 0, when v is equal to 0. Okay, so we will think about later on.
Yes.
So if you think of this, then we will see that the Laplacian will give you, of v cube will give you an extra term, which is like kinetic energy, which will involve the gradient square.
Absolutely.
V gradient square. So if we look at it from this point of view, perhaps this is an alternative way. I'm not, this is like, I've written some, like scribbled a few things while we were talking.
Yes,
and
yes,
then the alpha zero, which is, it seems that the right hand side, which is alpha zero or alpha zero multiplied by v of t or something like that, if you change the alpha zero by this term that is missing from the Laplacian v cube, perhaps there is something there that is fundamental that will come out that will be similar to some of the solutions that you have, but like maybe in an alternative way, or maybe perhaps even easier way. I don't know, but this is the way I'm going with you.
Yeah,
and I don't know, what's your opinion about this?
Absolutely, Fathi, thank you very much, because in fact this trick is really fundamental in this work, and let me show you how it works. So first of all, maybe please tell me if I answer your questions, or if I'm confused about it.
You're already done when you said yes. Okay, it's an opposite question anyway. But anyway,
okay. Let me tell you.
Okay, go ahead.
Yeah.
Please.
So first remark, and this is what you said probably. If you take initial data which doesn't depend on space, so you remove the Laplacian, and in that case you have v prime equals negative a constant over v square, and this gives you the rate with 1/3, because the solution of this guy is t to the power 1/3 multiplied by some constant, or capital T minus t to the power 1/3. So this is how you see the 1/3 coming. Then after that, what happens, as I told you at some point, in fact, I like blow-up problems. So when I see this, I'm not comfortable, and I would like to introduce, and this is something that can be done easily, as you did it during the talk. Introduce u, which is 1/v to the power alpha or beta, for any beta. And when you do that, in fact, you will see that depending on beta, you will see the following PDE that appears. Let me show it to you. I'm sorry. Yeah, I'm almost at the good. Yes, this is the PDE that we will see. I don't know exactly which value for beta, but you see, in fact, the Laplacian. No, this is not the good. This is not the good. No. This is maybe the good one. If you allow me, please, to take this equal to 0 and this equal to 0 and forget about this. So in fact, when you do that, you will see that you will find a solution where you have this gradient u square divided by u, and that comes from the fact that you have Laplacian of the v to the power 3. Yes, it will involve this. And in fact, we make the proof in this setting. Although we have this nasty term, we prefer from maybe, I think that the control of the spectral, yes, this is really important. The spectrum, the control of the spectrum of a blow-up problem is easier than the control of a spectrum of a quenching problem, meaning that if you have a solution, a PDE where V is going to 0 and you linearize around the profile, then you will have a problem of controlling the outside part where we are far from the touchdown problem. Now, if you make 1/u or 1/v and you call it u, you end up with a blow-up problem, and you will have a good control for the part which is outside the singularity. And this term was and is still very difficult to control, because in fact it involves, it's non-linear, gradient u square, it's divided by u, because although u blows up at the origin, far from the origin it will go to 0. So it's not easy, and we need more control. Yeah. Thank you, Fathi.
That's great. Thank you.
Please, Fathi, please. I'm really sorry, because the discussion is very beautiful, and but I have to stop the meeting. because
just one word. Just one word. Hatem, do we communicate? Please pass the information for Hatem. Best my
you can discuss out of this.
Inshallah. Thank you.
Thank you.
Merci.
Thank you.
Thank you, Fathi. Thank you, Nabil.
Thank you, Hatem. We'll discuss more about this, inshallah.
Inshallah, Fathi, of course, with great pleasure. With great pleasure.
I sent my email in the chat.
Yes, please. I will write to you.
I already did.
Okay.
And for everybody, we can meet in 2 weeks, inshallah. Okay.
Inshallah. Okay.
Salam. Merci يا حاتم. جزاك الله خير.
شكرا فتحي.
ميرسي
نبيل.
شكرا لك. مع السلامة. باي.
مع السلامة.
مع السلامة.